Welcome to the Pott College Faculty Colloquium Series. The Pott College Faculty Colloquium Series is offered once a month during the fall academic year. The series offers the opportunity for faculty to discuss their recent publications, their research, and their thoughts on teaching. Each colloquium series will include a wide range of topical areas from faculty who received internal grants. More specifically, the Pott College Science, Engineering, Education Research Grant, or the SEERGA Award, will be the colloquium series for the fall semester. Our first speaker is Dr. Todd Nelson, who will talk to us about origami-inspired morphing structure and developable mechanisms.
Thank you, Dr. Bauer. I'm pleased to be here. Thanks for coming out, for those of you who are in person and for those of you who are attending virtually. It's good to be here. I'll be presenting, as Dr. Bauer mentioned, on origami-inspired morphing structures and developable mechanisms. And it's a bit of a mouthful, but it is a pretty interesting topic that I enjoy, and I hope you do as well. So let's see here. And if I could get this, well, nope. 1 second. When I can get to go to the next slide, we'll resume slideshow. That's probably it. Yes, all right, we're in business. All right, so I got it. Okay, thanks. So I would like to first off acknowledge just the Pott College, University of Southern Indiana funding for this award, the SEERGA grant, and it's not going to work. Let's see here. Well, all right, yeah, and it's a little touchy on the slide projector. So, and also my collaborators, Luis Baltimore Pinto, he's a student here, a former student here at USI, as well as I had also collaborators from Brigham Young University, Idaho, the Beijing University of Aeronautics and Astronautics, and the Brigham Young University Compliant Mechanisms Research Group. So when I say origami, most people think of this, right? You made origami jumping frogs, maybe you've made some paper airplanes, you might have made some other types of fun cranes, things like that. And yes, indeed, this is origami, right? Origami can also take a little bit more complex forms, like this frog. So this frog is made from a single sheet of uncut paper and just folded. It was designed by Robert Ling, who's one of the top origami artists in the world. And you can see the detail that he's been able to capture. So he's got all 4 legs, plus in addition, now he has toes on each of the legs, and you have the body contours. And you can get a lot of detail in these origami models. It's just incredible what artists have done in the past with this origami. So you may be wondering, what is an engineer doing with origami? Is he bored as this, trying to fold things up? Well, origami actually has some great applications in engineering. So for example, there's lots of times when we have to take something that's very compact and stowed, and then in one position, such as a rocket launch, and then once it's up into another position, it needs to deploy out into a large spatial area. So we have a nice origami-inspired array up in the top left corner. Down in the bottom left corner, this is a hard stint. So it folds up into a small package that you can insert into an artery or vein. Once it gets into position, it expands out and it locks, and it maintains that opening for the blood flow to go through. And then over here on the right is a ballistic barrier, an origami-inspired ballistic barrier. So this one right here, and it shows the paper pattern that inspired it, and then we transition it to origami materials and into a 3D structure to make a barrier that you could potentially put 3 people behind and still stow in your trunk for police and law enforcement. So you might think, well, that's awesome. We take a piece of origami and we go straight to an awesome engineering application, but there's a little bit more to it than just that. For example, one of the first things you encounter is the thick folding problem. This is a problem we wish we all had, right? And it's where you have more material that you have to fold than just a single sheet of paper. Paper is paper thin. There's a reason we have that term, right? It's assumed to be 0 thickness. You can fold the paper on top of itself. I don't know, wasn't it like 7 times before it stops? So you can assume in all your modeling of origami that everything is paper thin. Well, when you move to a solar panel or a piece of metal or something like that, obviously you can't fold it just like you would hope. So you have to address these issues. This is there's a variety of ways you can address this thickness problem. This is one of them. So you see here, these have rolling joints on each of the offsets. And so when it's collapsed, all the panels line up and they stack nicely. And that's pretty tricky to do with thick panels. And then when it unfolds, all those panels are in a single plane. They're all lying in a single plane. And the reason that's possible is because of these rolling contacts. They're actually moving your axis of rotation during the motion. There's other ways you can do this. You can offset your hinges. You can taper your panels. There's a variety of thickness accommodation techniques that people have come up with. There's also a couple other origami problems that are tricky to deal with. And one of them is you notice the number of joints. There's a lot of joints in this mechanism, and they all have to be lined up just right. If one of them is off, it will lock this mechanism up and it won't move. And we call this an over-constrained mechanism. So it's, if any slight tolerance there, it will cause this mechanism to fail. So, and that's what origami is a bunch of chained mechanisms together. And if one of them fails, then it has repercussions. So you have to do different things to take care of those over constraints. What I'd like to focus on today is an aspect of origami you might not be quite as familiar with, and that's curved crease origami. So almost everybody, I assume you've folded papers hot dog style and hamburger style, and I don't know, maybe like animal style if you're going to In-N-Out or something like that. So but you may not have folded along curve before. And I mean, it's a pretty simple idea, right? You're just folding a paper along a curve. But when you do that, you end up with curved panels. So for example, this pot over here on the left, we fold along a curve, we crease along a curve, so you kind of pinch the paper along a curve. It makes these nice curved panels. So in this scorpion, you've got this, you got nice organic features, these curved panels that are enabled by these curved folds. Or if you're looking at these the cat eyes, we have those curved folds right around the eyes that allow that depression. Looks very nice and organic. So curved folding really is you can understand it in simple parts, which is nice. We can start to dissect this. So when you fold a piece of paper, you really can only get three things. You can get a cylinder, so you can fold it into a cylinder. You can get a cone, you can kind of make your paper into a cone shape. And then there's one other style, it's called a tangent developable surface. And this one is a little more complex, but it's a little harder to fold, but it's also a possibility. And these are all tied together. They form from a flat sheet using just bending or folding and no stretching or tearing. So it's origami, right? That's what the definition of origami is. So if we take these, we now have a nice way to look at it. We have this lens to look at curved folding. And you're pretty tied together here. Oh, and I should point out, there's a special quality called ruling lines of all these things, where when you make it, you can take a ruler and you can place it on the surface, and that ruler will touch the surface along it. So that is a ruling line. And anything that comes from a flat sheet will have those ruling lines. Yeah, and you'll get what's called a single curvature surface. So we can start to be a little more creative with these, and we can piece them together. So we can kind of play like a puzzle. So here's a car body, a concept car body that came from a flat sheet, and it's folded together where you have tangent developables, you have cylindrical pieces, and you have conical pieces all patched together to make a more interesting structure here. In addition, you can also have these ruling lines aren't fixed in a surface. As you fold, they can move, they can shift, and that allows a large variety of surfaces to be met. So the work that this SEERGA grant was inspired from this idea of using thickness accommodation in curved crease origami. So this was some prior work I did during my PhD work, where I took these curved crease origami patterns and tried to move them out of paper into something else. And for example, here's a curved crease piece. This one's called Elliptic Infinity. It's an origami piece, once again by Robert Lang. But instead of being in paper, this time I took it and changed it into wood. This is MDF. It's MDF that's been laser cut with this very specific pattern where it lines up the bending along the ruling lines, and you can get wood, which normally does not go into this shape, to go into a nice pattern here. And along the major crease lines, I've used a material called bulk metallic glass that's has really good properties. It's kind of like glorified tinfoil, if you want to think of it that way. So that enables those large creases. So you can see a video of it here moving. So it goes from a flat sheet into a nice form shape, and then comes out. So this was just a nice example of how to accommodate thickness. So once we had a way to accommodate thickness, I thought, well, why not? Can we match a specific profile? Like I've got a way to make panels bend into what I want. Can I get them to go into the exact shape I want, not just like a general panel bending? And that's really what the objective of this SEERGA grant was to achieve a desired deployed shape from a flat sheet through 2D geometric patterns placed in the sheet and a simple deployment method. So, all right, so it's where you take this deployment method and it's just a compression method, and you can get your panel to go into a sheet. So the possible applications for this are stowable reflectors and antenna for space mechanisms, tunable optics, morphing aerodynamic or hydrodynamic surfaces, conforming structures or components such as a circuit board to a curved surface. So if you want your circuit board to bend instead of be a nice flat panel. I decided to start with just the simplest developable surface, and that's cylinders, right? So I'm not just constraining myself to a cone, but any sort of cylindrical shape that just has parallel ruling lines, and we call that a generalized convex cylindrical developable surface. So that cross section, that green line, is what I'm trying to target. I'm going to try and target a specific profile. And it ends up that you can model this. You model your surface as just a series of rigid and flexible regions, or rigid and compliant regions. And you can draw a nice free body diagram for those of you in the engineering fields. And you can actually solve for what the springs are represented by the little curlies. You can solve for the stiffness of those springs, what it needs to be in order to achieve a nice profile shape. And we're just squeezing on these two things. We're actuating two opposing tip loads to get to form into your shape. And those opposing tip loads could be a lightweight cable. You could be a clamping device, any sort of simple actuation method, a contractile element. And now comes the question, well, if you can solve for what those stiffnesses are, what should you pick what kind of geometry can you get to come up with those stiffnesses? And where should you put them? Where should you put these springs in your profile? And so we looked at where you want to put these springs in your profile. And to do that, we came up with a measure of air. So my desired surface is the light gray surface on top. That's what I want to try and match. My series of rigid bars was connected with springs. That's not going to be exactly that nice curved desired directrix. So instead, I get an actual surface that's just a nice segmented line. And I have two measures of air that I can develop. And that is the aerial profile air. That's the red region between the desired and actual surface. And then also this lineal profile air. That's another type of air I can define. And that's just a distance measure. It's like the worst case scenario between my desired and the actual surfaces. So when you have a way to measure the air, you can start to optimize where you place these. And I did this numerically, wrote a computer script to help me minimize these errors. And we came up with an interesting result while doing this. So if you're trying to match a parabola and you want to minimize the difference in area between a segmented line and a nice parabola shape, it ends up that the spacing of your joints is exactly equal. So you can notice the joints are the circles. They're placed every 2 inches in this case, apart from each other. And that is what's going to it's going to minimize your aerial air. And we showed this mathematically, we proved it mathematically that this is indeed the case, which was kind of a unique side finding from this project. So once you had where to place your springs, the other issue is what can you use as a spring? And that leads us to compliant joints or flexible joints. And we chose to use this laminar emergent torsion joint is what it's called. And you can see up here on the right, this is a joint that if you twist it, it twists the bars. There's 4 bars, and those bars twist as you twist this complex. And by changing the geometry of those bars, so by adjusting either their width or their length or their thickness, you can make them behave like a spring with a custom stiffness. And the nice part about these patterns, it's a 2D geometry. If I keep the thickness constant, I can just cut out different geometries to get different spring stiffnesses. So now we had a way not only to place our joints, but also how to achieve their stiffness. And that led us to, well, let's try it out. Let's see if we can do it. So we took an airfoil shape. So this blue line represents the top surface of a Clark wire airfoil, which is just a common airfoil for small scale aircraft. So we have this Clark wire airfoil, and we gave some parameters to our model we developed, and we calculated out the geometries we need to see if we could make it match that profile. So we made this one out of polypropylene, just a plastic, and we laser cut it up at the Applied Engineering Center. I'd like to thank Justin Amos for his assistance with that. And we tested this to see did it indeed match the profile, and it matched pretty well. It matched with an error of about 36 thousandths of an inch, which was acceptable for us. So we thought that was pretty good. We also did it with in a metal substrate. So we did it with aluminum 775, T6 aluminum 7075 in the shape of a parabola. So a nice reflector that you could use for communications or directing a light source. And in this case, we came up with this geometry, which was laser cut, or which was cut on a water jet once again here at the Applied Engineering Center at USI. And it makes this nice parabola shape, which when you shine light on it, it focuses the light right there at the focal point. And so you can see that this matches really well. And I've actually brought that one today. For those of you who are here in person, you can check it out and you can try and match up to the profile and see how it works. So. All right. So after doing this work with matching surfaces, we thought, well, and this is the second part of the SEERGA grant, which we're still currently working on. And that is, well, can you integrate a mechanism directly into a surface? Now we're able to curve surfaces. We can make them match profiles we want. Could you put a mechanism inside the surface? And we called these, we named them, came up with a name for them, because though this has been done before, it's never been really studied concretely. So we gave them a name, developable mechanisms, named after developable surfaces, these surfaces that come from a flat sheet. And these are mechanisms that reside in or conform to a developable surface. They're very compact, and yet they can have really complex movements. So you can build your mechanism right into the surface. So here on the left is an example of one that's residing on a surface, it's just kind of attached to it. The other one is integrated into the surface. And we looked at these and we said, well, what's the theory behind these? Can we get a mechanism that works? Because it's not as simple as just, like, oh, here's the mechanism I want, let's glue it onto the surface, right? It doesn't quite work that way. We tried it, doesn't work. So yeah. So instead, you have to use a little bit of knowledge about developable surfaces. You have to use those ruling lines I mentioned, those straight lines that you can put a ruler on. If you align your hinges with those ruling lines, you can make, and you design the links, you can make mechanisms that will move. And so here's an example of a piece of galvanized steel with a nice 6-bar mechanism on it that morphs out. It's a pretty complex mechanism that morphs out of the surface there. And these ones we just use tape hinges to demonstrate on, but I'll show later that you can use other hinges built into the surface. And there's a nice correlation with these developable mechanisms with already developed mechanism theory. So really there's 3 major types of mechanisms. There's planar mechanisms where all your links are in a plane. Those happen to correlate with generalized cylinders. There's spherical mechanisms where all your links travel on spheres. Those correlate with conical developables. And then finally, there's spatial mechanisms, which are where your links are up in space, and those correlate with tangent developable mechanisms. So we came up with this way to connect mechanism theory that's already very well developed with coming out of a plane with developable surfaces. And that really opens up a lot of spots for you to innovate and to create mechanisms that have multifunctionality that are really compact. And here's just an example of one where instead of using tape hinges, we've actually integrated the hinges using those twisting torsional joints right into the mechanism itself. And so you can think of it as like a nice little piece of Iron Man armor, and out pops something from his arm, right? And that movie's awesome. I look at it, I'm like, man, how did they fit all those mechanisms into that suit? I still haven't quite figured it out, but this is a start, right? It's getting towards it. So in conclusion, we have origami and origami-inspired techniques can provide an opportunity for these hyper-compact mechanisms with complex movements, morphing behaviors targeting specific shapes, and innovation in products used by or on our bodies. You can think about wearable electronics, wearable exoskeletons. We can have devices in our bodies, heart stents. You can have laparoscopic surgical devices. We can use them in the air, on aircraft. We can use them in the water, on ships, and beyond, up in space, right? And the possibilities here are just, they're exciting, right? You can take this artwork, which has been, artists have been developing these awesome fold patterns for centuries, and we can apply it to an aspect, a very challenging engineering problem, and come up with a very elegant solution. So it's a very nice crossover between the fields of art and engineering. And with that, I'd like to thank you for your attention.
All right, do we have any questions?
Yeah.
How long does it take to make, like, how long would it take to, like, make, like, one of your pictures?
Yeah, so, well, it depends on which one you're talking about. So like for the morphing surfaces, for these kind of surfaces, the design, once you have your MATLAB code all running and all your model up running, it's really not too difficult to come up with the design. Usually though, it takes a little bit of tweaking of parameters. So you have to watch out to make sure the stresses don't exceed the yield stress. So like it'll pop back to shape once it's done. So that does take a little bit of fine tuning parameters. You have to adjust thicknesses and lengths in order to get what you like. But once you've got your design, making it is actually not too hard. I don't know, Justin, what do you think? It took 20 minutes? No, it took longer to cut this one out.
That one took a little bit longer. A lot of starts and stops.
Yep.
Program that is about runtime, probably around that 20.
Yeah. Yeah. For the other ones, for these guys, like the 3D printable ones, the design can be a little bit trickier. You have to watch for, there's other aspects. It's not quite as simple as just choosing ruling lines to put on your hinges. That gets you a long ways, but then you have to look at how you tying your links together. You have to watch out for interference. You have to watch out for singularity points where your mechanism will get stuck, essentially. So you have to draw on what's already developed in the mechanism field to be able to do this. So, yeah, but 3D printing it doesn't take too long. Just a normal 3D print. I mean, this one probably is like a 4 or 5 hour print to get it there. Yeah.
So how did you go from, like, to that? Did you put it in, like, a modeling software? Did it to the 3D print out or something?
Yeah. So I wrote my code in MATLAB, which calculated all the distances. And then I took that MATLAB code, I outputted like a file, just a list of the numbers, right? And I use a program called Rhinoceros, which is similar to like a CAD modeling system like SolidWorks, where you can put in your distances and then it actually generates the lines for you and spits out the pattern for you. It's like kind of coding, visual coding, you could call it, CAD software coding. And so I hooked that model up with my MATLAB model so I could generate these patterns pretty quickly. Initially, the time to do that takes quite a while, but once it's working, then it becomes pretty fast.
4-bar springs. How much of that is math and planning versus trial and error?
Yeah, so for the morphing surfaces, it's much more math than trial and error. You can solve for these exactly. So like it's just getting the right inputs into your math model to get your behavior you want out. For the mechanisms that reside on surfaces, that is a lot more creative endeavor. You have to choose, there's a lot more free choices you can make and a lot more. So for example, there was one of the mechanisms that came out of this work was a laparoscopic surgical tool that cleans off the end of the camera. So it's like a little windshield wiper that's built into a cylinder that just wipes off the end of the camera. So if like bodily fluids get on it, it just cleans it off. So that one, I mean, it takes some creativity to come up with, hey, where's this application going to be used? What type of linkage should I use? And that takes a little bit more creativity and thought. Anything else? Where do I hope to go from here? Oh, to the moon now. So, I mean, I like how diverse the applications are. So, I mean, I've been able to do some work in the medical fields as well as in aeronautics and in space. So I really like the kind of getting my hands in everything. So to an extent, right? And so really just comes down to like, if you see an application, I'm always trying to look as I like move around, you kind of get used to like watching for, hey, like there's a surface that's popping out or I could, if I put a mechanism that did that incorporated into the table itself, like what could I gain from that? So you start to look for opportunities and look for those things as you live, right? And then that's where it takes you.
All right, thank you, Dr. Nelson. We will include future presentations on our website. We'll have one next month in October and November, and I think we have one scheduled for December as well. So thank you for joining us in person and also YouTube Live. We will have this recorded and put on our website. Thank you.